Okay, so let's talk friction. So everybody click and close, all the way close, please. You'll get a chance to do a little work here, maybe. I don't know. We're going to complicate our discussion. Click and close, all the way. Okay, so let's review real quick what we did yesterday. Yesterday was pretty profound. We did some important stuff. Okay, what we found yesterday was we ended up getting results kind of like this, didn't we? So if we were going to track, we were going to compare static frictional force, right? So we'll call that F sub S. What do you need to change? Password? For which one? Algebra review? Which one? And is NMN. Okay? Thanks. Okay, so we compared static frictional force necessary, or the maximum static frictional force that we saw compared to the weight of the sled, right, that we were pulling, weight of the block, call it a sled. So, mg. Well, actually, but what was that meant to be? For us, it was just normal force, right? Because the forces were horizontal. So if we were to draw a free body diagram of yesterday, what did we get? There's the block we were pulling. What are the forces acting on the block? So gravity is pushing down.
Normal force is pushing up.
Normal force is pushing up.
Friction is going back.
So let's say, I guess we were technically pulling this way, weren't we? Right, so then we have the tension, and then friction is pulling this way, right? So there's our static friction. Okay, so vertically, these two forces were equal. When the thing was at rest, which it was until it broke free, right? When it was motionless, that means the net force had to be zero, because there was no acceleration, right? So we know that the normal force was always equal to the weight. So what we measured, when we measured the mass of the sled, we were able to calculate its weight, and we were indirectly calculating normal force in that case, right? So we were comparing normal force to the static frictional force that resisted the tension. Think what we did. I just increased the tension progressively until finally it broke free and slid, right? And so what we did is we looked on those graphs and we just saw what was the peak tension force right before the thing started to accelerate, right? And the tension force got smaller, right? And so we measured effectively then tension, the maximum tension that we got in the line was equal to the maximum static frictional force that the table provided, that acted between the table and the sled, okay? And we saw that when we did that then, we got some data points, and they looked basically, it was pretty linear, right? I mean, it looked kind of like, for most people, I think it looked, well, same for everybody, it looked kind of like that, right, ish. So it was pretty good and linear. We saw that then if we were to calculate the best fit line, y equals mx plus b, what was our, instead of y, what was our vertical quantity? Okay, static frictional force, right? So we got static frictional force equals the slope times what was x?
0.3.
Normal force. The slope was something like what was the slope? 0.3019 or something? 91. So, close enough, right? Something like that. Times x, which was the normal force, right? That was our input value, input quantity. And then b was something like 0.1. So it was pretty small, right? What were the physics gods probably trying to do there? Go to zero, right? So ideally, if this had been done perfectly, the points would have lined up exactly in a line, and the line would have gone through the origin, okay? Now, nothing's ever perfect in an experimental situation, but honestly, for a high school classroom, that's pretty good. So this is really meant to go to 0. Okay, so then this tells us something really important. This tells us that the slope of this line, which is really just the ratio between the static frictional force and the normal force, if I solve for this quantity, 0.3091 is equal to the ratio of frictional force over normal force. That must be a property of the materials, right? And that's what we call a coefficient. That's the static coefficient of friction. We said yesterday, or day before, when we talked friction in here, that there were a couple factors that would have impacted the frictional force, right? One of them would have been the normal force. The more strongly two objects are pushed together, the more actively their little knobbies interact with each other, right? And they stick together more. They kind of weld together more strongly, okay? The other thing must have been just the materials themselves, right? Well, what we found here is that, yeah, the normal force certainly plays a role. The frictional force is proportional to the normal force. If we double the normal force, we indeed do double the frictional force. But the constant of proportionality, that's the part that's dictated by the surfaces, okay? Does that make sense? Okay, so this is going to be a number. You can almost think of this as being the percent of, like if I'm pushing down, if the surfaces were perfectly, how do I want to say this? If they had really, really high frictional coefficients, then as I push down on, or as something sits on the surface, if the friction was really strong, I should expect that I'm going to have to pull with the full weight of the object to make it slide, right? Does that make sense? Like if the object has a weight of 10 newtons, I would theoretically, if the friction were really powerful, I'd have to pull with a full 10 newtons to get that thing to slide, right? Because it's gripping, the surfaces grip very strongly. Well, that would correspond to a coefficient of 1, right? If there's a very weak frictional interaction, then I shouldn't have to pull with a very large percentage of the weight to make the thing slide. So this is really kind of like just telling you how effectively is the material translating the downward normal forces into horizontal frictional forces. So here, about 31% of the downward normal force got turned into a horizontal sideways force. That's how vigorously they interact with each other. So what do you think the lowest possible value for a frictional coefficient would be then? I mean, 0 would be the limit, wouldn't it? Right. You couldn't get negative. Why would negative make no sense?
Because it would just go on its own.
It'd go the opposite way. That wouldn't make any sense, would it? That's not physical.
That would make it go
faster. If you're going to pull this way, exactly.
It would just
so the friction
keep
would tend
on going.
to, that's not how friction works, right? So the lower limit is obviously 1. What's the upper limit? 1. Okay. Yeah, they always say 1 in physics books. It's not really 1. You can cheat. I mean, materials, and I know it's kind of cheating in a way, but like if you put a rubber block down on a rubber surface, it actually takes more force to slide the rubber block than it does to pick it up. Because I mean, it sort of cheats in a way. There's a little bit of almost like adhesion there, right? The material is so gummy that it just conforms so well that it actually, I mean, like you can imagine that if you picked it up, it would make kind of a sound, right? It would sort of stick to the surface, right? It creates little air pockets, and the little air pockets, the air gets expelled, and so you get, it's like a little suction, right? You get some low pressure spots in there that suck it down even harder. So it's kind of cheating in a way, but I don't know. I mean, is it really cheating? Maybe not. Maybe not. Oh, okay.
What's the coefficient on? Yes. What's the coefficient on Velcro?
Velcro is definitely cheating. It's definitely cheating because they're, all right, you betcha. Because with Velcro, you got little hooks of material that are literally tying into little loops of material. It's hook and loop. So that doesn't really count. Velcro is definitely cheating. That's not really friction. Okay, so but let's look at something here. This has a really profound implication about, let's go back to cars. Cars are a great way to explore physics. Think about car design. I've got a friend in college, one of my best friends in college ended up being, he's a physics major with me, and he ended up going into mechanical engineering with cars. And he's worked his whole career, mostly in Florida, I think, but he's worked designing like the cars that you're going to drive in 60 years. I mean, these are where he just works on really high efficiency internal combustion engines. You know, he works on really advanced, he works with materials researchers, and everything he does is just based on how you're gonna make a car, what's the ultimate car gonna look like. And so I think I don't know, it's just kind of a fun way to think about this. Let's think about the importance of friction in driving. I mean, obviously, what's the big, where is friction crucially important when you're driving a car?
Tires to road.
Okay, it's what holds the car down to the road, which is important because you gotta be able to speed up and stop, you gotta be able to turn also, right? Okay, so let's think about stopping, and we'll come back to this discussion again and again for the next month or so about stopping. When we talk about energy, conservation of energy, stuff like that, we can revisit this and have even deeper insight. But for now, let's just think about what it takes to stop, okay? So let me grab, I've got a little table of coefficients here. Let's look at let's just take this table, and I did in-depth research to find this. I just Googled something. Yeah, frictional coefficients, tires, and I got this. It's really tough. Okay, and let's do a little comparison here. Let's figure out if a car is traveling along the road, let's try to determine how much of a difference it makes if you're able to, if the car skids on the concrete, and we'll even make it dry concrete. So this would be the best situation for skidding you could get. It'd get a lot worse if the material were wet or icy. This would even be more dramatic. But we'll take the most conservative way we can. We'll take the place where it would hurt you the least to skid, and we'll still show that skidding isn't a good idea, right? What are the ways you could brake to a halt in a car if you were, just imagine you're in the car and you want to get to a stop as quickly as you can. If you just jam your foot on the brake and it's an old car without anti-lock brakes, what happens? They lock up and you slide. Kinetic or static friction? Kinetic. Okay, now, and this is confusing sometimes because you think you lock the brakes up, so that sounds static. But when we're talking about friction, we're talking about the two surfaces where the friction is happening. So yeah, the tire is locked up relative to the car, but relative to the road, the tire is sliding, right?
And when the tire's still rolling, it's static. Okay,
good. So it's going to be, when it's a skidding stop, that's going to be kinetic friction. If you do a rolling stop, that's going to be static, because even though the tire is moving relative to the car, the surface of the rubber is not sliding on the pavement, right? And so there's two different ways you could do this. You could either just slam on the brakes, or you could do a threshold brake, which is where you're somehow going to try to prevent the tire from skidding, but apply the most possible braking force, right? Does that make sense? So the tire doesn't skid, it rolls, but it's still stopping the car. Okay, let's compare those two, and let's just see what the percentage difference is in the stopping distances for. Let's take a car. We got rubber on concrete or rubber on asphalt. Let's do concrete, right? Asphalt is the black stuff. Concrete is when you're driving down the gorge. You're driving down 84. There's some places where the road is kind of light, right? That's concrete compared to asphalt. Asphalt's the dark, the black stuff. Okay, so then we get these coefficients. So we know that on dry concrete, kinetic coefficient is 0.68, static coefficient is 0.9. Okay? So we could put in some numbers. Like we could say, well, what if we're traveling, the equivalent of, well, let's just say, well, let's put in some numbers. So if we're going 70 miles an hour, somebody real quickly tell me what that is in meters per second. Get on your phones and tell me what that is in meters per second. Make it 75. $31.293. So we'll just say, how about we'll say 32.
33.52 each.
33. Oh, what is it?
75.
Yep.
Also,
33.5.
Okay, so 33.5. 33.5 meters per second. The final is going to be 0, right? And we want to know what the stopping distance is going to be, right? So let's say our car has a mass. What's like a regular car going to be? Like a 3,000?
500 pounds.
it's gonna be 2 tons.
I mean, like a truck might be 3 tons.
I'd say.
Let's say-
My car is
1.5
3,800
tons.
pounds.
How much is your car?
3,800.
Okay, so let's say slightly. So let's just say 2,000 kilograms. That'd be 4,400 pounds-ish, right?
Yeah.
Average car.
So the mass is 2,000 kilograms. When we look back at this, we'll say, gosh, we really need to pick all those numbers, and we'll see maybe a cooler way of thinking about this. But we'll just pick numbers for now. And so we want to know then what the stopping distance is going to be. Well, that's going to be determined by the acceleration, isn't it? Right? Everybody agree? Okay, so our free body diagram looks just like the one we had. Looks just like that, right? Instead of tension, though, well, not quite like that. We'll draw it. So what's our, if we're traveling to the right, let's say, in the positive x direction, what are the forces acting on the car then, when we're slamming on the brakes? So gravity, it's a level road, as most are. Normal force. Forces.
Friction.
Friction. That's it, isn't it? Right? If we're slamming on the brakes then, there's only one force acting horizontally, and that's friction. Right? That make sense? Okay, so let's go up with our equations of motion then, right? So we're gonna add up the net vertical and horizontal components of the net force, right? We're gonna find those. So what's our vertical equation of motion? So the net, the y component of the net force, what are the forces acting vertically? So not net, what do we call it?
Gravity.
Normal force is positive, minus,
Gravity.
and what's the vertical acceleration? 0, right? So ma is just 0, right? So normal force minus mg equals 0. What's probably a better way of saying that equation? Normal force equals mg, right? If I just isolate normal force. Okay, so that's important. We kind of get that by now. If it's level, that's right. That's the situation. Okay, horizontally, there's only one force acting, right? Horizontally, the net force is just minus friction, right? Okay, so what's the friction going to look like? Well, friction is, we alluded to this before, but let's, I guess, say it. What is our equation for friction? So for frictional, this is our simple frictional model. So frictional force, if it's static frictional force, let's do kinetic first. Kinetic frictional force is just going to be that coefficient, right? Call it mu sub k times normal force, right? Now what about static frictional force? Static frictional force is just a little bit trickier. Static frictional force, like if I'm pushing on this mass right now with a force of 1/10 of a Newton, I'm pushing that way with exactly, I'm a trained physicist, I'm pushing exactly 1/10 of a Newton. So what is the static frictional force? 1/10 of a Newton. How do you know?
Because that's the force that's pushing back. Well,
When you can tell by looking at it.
because it's not moving.
Because it's not moving, so the forces have to balance, right? If I push with 1/100th of a Newton, it only pushes back with 100th of a Newton. Okay, I can push with more and more and more, but at some point it's going to break free, right? At some point it can't push back with the same amount of force that I'm pushing on it with, right? And so then the static frictional force, we would say something a little different. It's going to be greater than or equal to 0, right? Well, it's not equal to, that doesn't really make any sense. Greater than 0. for it to be a force, right? And it's gonna be less than or equal to whatever its maximum threshold is, right? Well, what's the maximum threshold? That's gonna be dictated by the coefficient of static friction, right? Coefficient of static friction times normal force is giving us the maximum possible static frictional force that could be provided between vinyl surfaces. It'll always counteract any sideways motion up until that point, and then it can't anymore, it breaks free. So another way of saying that would just be that the maximum the maximum static frictional force would just equal mu sub s times normal force. Okay. All right, so then let's go over to this page over here then. So we end up with the net force horizontally is just negative F. It's acting in the negative direction, it's got a force of F. And that's equal to MA, right? We know that F is really just going to be mu times normal force, and that equals MA, right? And so if we solve for A, what's A equal to here then?
Negative mu times over normal force.
Okay, mu times normal force
Divided by mass.
divided by mass. And what is normal force? Yeah, we know from the vertical equation of motion that the normal force is just the weight, right? So this is equal to negative mu times mg over m.
You can cancel the ends.
Yeah, we can cancel the m's, and so we get something pretty simple. It's just negative mu times g, isn't it? Right? Okay? Now, if it's static frictional force, that's going to be mu sub s. If it's kinetic, it's going to be mu sub k. All right, so let's come up with two different answers here then. So my static acceleration would equal negative mu times g. So somebody do this for me real quick. So what is 0.9 times g?
Somewhere around 0.81. Isn't it?
So what is that up to, like 3 places? G. 9 times 9.8. 0.9 times 9.8.
8.82.
Okay, 8.82 meters per second squared. A sub k is going to equal negative 0.68 times g.
It's gonna be 6.66.
Okay, so that's giving us back. That gives us back the decelerations, right, that the friction can provide. Okay, the negative accelerations. So now let's figure out what the stopping distances are. Whoops, so there's our accelerations, and then what do we say, this is our initial conditions right up here, so we'll grab those. Okay, so let's go to work then. So we know acceleration, we know initial and final velocities. What are we trying to find?
Distance.
Displacements, right? Okay, so in general, which equation is gonna link all those things together? Close that Chromebook up. Close that Chromebook up. Which equation are we gonna use? Kinematic equation? Not 2. 4, because there's no time, right? Okay, so 4 tells us what? V final squared minus initial velocity squared equals 2a delta x, right? And we're trying to solve for delta x. So delta x is just going to equal V squared minus V naught squared over 2A. Good?
Yeah.
Okay. So we'll try this then. We'll try delta X for static friction. Let's calculate that. So what do we get? Negative 0 squared is 0. Negative 33.5 squared divided by 2 times negative 8.82. What is that?
63.6
What are the units going to be?
meters.
Meters. Okay. And what about delta X sub K then? So we're going to get same stuff, only different coefficients. So negative 33.5 squared over 2 times negative 6.6. There we go. What's that equal to?
84.3.
84.3 meters. Okay, so that's, let's compare those then. How much of an increase is that? So 84, so this is what we're comparing it to, right? How much, what's the percentage increase in stopping distance if you're locking up your brakes as opposed to not locking up your brakes? 84.3 over 63.6 is what? Somebody. 1 point,
Yeah, it's 1.3.
1.3,
2, 4.
3, 2, 4, so we'll just say 3, 2.
Yeah.
Easy movies.
Oh, man, why am I doing that?
Easy movies. It's like a line runner. You guys know the line runner?
Why is it like, I don't know why it does it sometimes. So that's a 32% increase in stopping distance. That's a lot, yeah.
How do we originally define the values of the slamming on the brakes and the not slamming on the brakes? Where do we get those numbers?
Static and
Chart.
From
Okay, just from the chart, just from
the
static
chart,
and non-chart.
yeah. So 32%, that's some, so that, I mean, that's adding quite a bit. 32% extra stopping distance if you're slamming on the brakes. Now, I want you to notice something here too. If we picked 75 miles per hour, what if we picked something like 50 meters per second? Well, never mind. I mean, I want to make this point. I want to save this for later. Okay, so I'll save this for later in class. But that's, we didn't really have to specify, did we? The point I wanted to make earlier to you guys is we didn't really have to specify an initial velocity, did we? Because in our calculations, notice that the initial velocity that we picked was this, was the same in both cases, right? We didn't really even have to specify a mass, did we? Didn't make any difference. We didn't have to, well, that's the only other thing I guess we specified. We could have just done this in terms of an initial velocity. It would have been almost cooler in a way to not have to pin ourselves down to a single value. And then what would have happened here is we would have ended up with a V naught squared and a V naught squared, right? And when we took the ratio of the two delta x's, instead of getting a ratio of numbers, I would have got something times V naught squared divided by something times V naught squared, and they would have canceled. You see that? So we could have done this independent of initial velocity. When something drops out like that of an equation, that's the math god's way of telling you it didn't matter. It doesn't. It's irrelevant. It doesn't impact the answer. The answer is insensitive to that value, right? Or the physics gods.
Yeah, all you need is
Okay.
the deceleration. It's the same exact. The ratio of the 8.82 divided by 6.66. It's the exact same.
Well, those are numbers we did have to use, right? Because those are properties of the two different types of friction, right? These are categories of friction. Okay, so this would have been, I promise you, and I'll have you do this, I think, on one of the assignments. I think you actually do this. If we did this with ice, the discrepancy would have been much bigger, because I think, like, if we go to this table,
Nice cheats.
if you look on ice, what's it say here? Rubber on ice is about 0.15 for kinetic. The static is probably going to be something more like, 0.2, 0.2 something. And so it's gonna end up being, almost double the coefficient of kinetic friction. So even though those are smaller coefficients and the stopping distance are gonna be much larger, the percentage difference is gonna be magnified for ice as compared to dry concrete.
Why does it?
So you have an appreciation for why anti-lock brakes are so important, right? 32% increase in stopping distance if you lock the brakes up. So now let's get practical and let's talk about cars. How do you do this in a car? How would you accomplish this? Because this puts you, physics we're theoretical primarily, so I want you to get used to the theoretical physics, but it's fun to think about this in terms of engineering too. Now, how would you actually accomplish this in real life? You got this theoretical physics point that we just made that's important, right? How do you accomplish taking advantage of that discrepancy? How do you take advantage of the fact that static frictional coefficients are so much higher than kinetic frictional coefficients? What would you do? How do you make a car do that, right? And you see what we're trying to do. We're trying to threshold brake. We're trying to get the car to not lock the brakes up. We want the car to brake as strongly as possible without skidding. So what do? There's kind of an inexpensive way to do it that's pretty effective that most cars use, and then there's a much more expensive way that only really high-end cars use.
Try pumping the brakes.
Okay, that is why back in the day, before there were anti-lock brakes, we were all taught to pump the brakes when you're in a car. If you're in a really old car, that's what you do. It doesn't have anti-lock brakes. You pump the brakes because, what's that do? Okay, it's gonna grab for a second, but then just as it starts to skid, you let go, right? And it rolls a little bit. And then as you depress the brakes, the rubber's gonna stick. And what does rubber do when it gets under high force? What does rubber do? Deforms, right? And so the rubber's gonna deform a little bit as it sticks to the ground, and then you let it go, right? Pumping the brakes, what's the problem with that though? Why is that
It's
probably
not the most efficient.
It's not the most efficient because you can't do it fast enough. And so what kind of the lower end, but still very effective anti-lock brakes do, and you can feel them do this sometimes if you step into your car has this time. They vibrate, don't they? What happens is when you engage the anti-lock brakes, when the car senses that the back wheels are turning at a different rate than, well, how does it do this? It would be like the wheels are turning at a faster rate than the car is moving, okay? So if it senses that's going on, then it's going to modulate the brake pressure in the lines really quickly. So it's just going to turn it on and off. And what that does, I think it's like 10 times a second is sort of the standard. So what it does then is the car is going to lock them up, the tires are going to stretch a little bit, and then it releases it, and they reform. They deform and they reform, right? So it's going to static frictional force, lets it go, clamps down again, more static frictional force, but it never quite skids. If it just starts to skid, it'll stop when they uncatch, right? When it modulates that brake line. Okay, that's pretty clever, and it works pretty well. What's the disadvantage of that? It's not perfectly efficient. What's the disadvantage of that?
10 times a second isn't as fast as possible.
Well, 10 times a second is pretty much optimal. But the disadvantage of that is there is a period of time where the brakes are completely, released, right? And so even though the rubber is pretty much continually like being pulled and back and pulled and back, it's not like it's applying a constant braking force the whole time, right? So it's good. It's definitely better than the alternative, which is just locking them up. But there's a better way to do it, and that's like really high-end cars would actually have an optical sensor that is looking down at the road that's telling you, it's measuring speed, and it's measuring how fast your tires are turning. And computers are fast. These chips are optimized to be really fast. And so what it's going to do is it's going to do a little calculation that's going to vary every time because different surfaces are different, right? Conditions are different. So when you put on the brakes, it's going to measure exactly what the amount of force is that requires those tires to skid for just 1/100th of a second, really short period of time. So you say, aha, okay, we got to back off from that, and we're going to make the force a little less than that. And it'll test that periodically. It'll go through a test phase, sample every once so often, so it'll keep readjusting that as the speed decreases, and it'll keep the car just right below the threshold of where it's going to skid. which of course is the best situation because then it's applying a constant force the whole time. Either way though, even if, here's the other part of this too, you gotta think like an engineer. Even if, let's say the modulated braking wasn't giving you a huge advantage over just skidding, right? There is one huge aspect that is even more important maybe than just the pure stopping. What's that?
Control.
You have control of the car, right? When the wheels are turning, you still can maneuver the car, right? If they're skidding, you can't at all, right? Once they're skidding, you have no way to change the direction of the car. So there's the other huge advantage of anti-lock brakes. Get anti-lock brakes. When you're buying your college car, get one with anti-lock brakes. They are huge. I mean, they make such a difference. And you should get a brake on your insurance when you get them too, so make sure you check into that. Okay, when are we at here?
5 minutes.
Okay, so I can't do the next example. All right, questions on that?
What about air brakes?
Air brakes. I don't know. I mean, I don't know. You mean like air brakes, like compression brakes?
No, I mean like they have a fin and it goes up.
Oh, yeah, that would be good. I mean, that would, so air brakes, like on a plane, yeah, air brakes, do they have those on cars?
Yep.
Really?
Nice ones.
Really? Huh. So air brakes would be a benefit because that's just like icing on the cake, because you still have the full frictional braking, but then the air brake is going to provide some drag. Drag's different. We'll talk about drag later.
That's better for higher speeds.
Yeah, better for higher speeds, right. Yeah. Why do cars, here's one for you. When you look at like racing cars or really high-end cars, why do they typically have an airfoil that's kind of, it would look like this? What's going on with this? This is a good related question. Okay, because friction is valuable in different ways. It's valuable to stop, but it's also valuable to like go around tight corners and things, right? So a really exotic car, a lot of times, they'll be real low profile, right? And then they'll kind of like that. But then a lot of times they're going to have some airfoil on the back that looks like that.
Downforce.
Yeah. Okay, why would it be providing downforce?
Because
These cars can go so fast they might generate lift.
Why is that? Well, okay, that's true, but there's an advantage. There's a huge advantage to having more downforce. What's that doing?
More
Easier-
friction,
easier to
just
get
so you can
friction.
jump faster.
Okay. Well, what's it doing to our free body diagram? Free body
There's
diagram.
more-
Let's say we're going around a corner, for example, and so the only forces acting are going to be friction. We're turning like this, right? So the frictional forces are having to pull us towards the center of the turn, right? So there's our frictional force. What are the forces that are acting vertically again?
Gravity,
Okay, gravity. Is that going to change?
no.
That's constant.
And then the normal force.
Okay, but what's the okay, so we got the normal force. What's the other force then? If we've got this fin that's deflecting air upward, what's that doing
Down.
vertically?
It's
Pushing
pushing
down.
down.
Okay, it's pushing down. So there's going to be some pressure downward as a result of the fin, right? So let's just call that F sub fin, right? So it's providing some additional downward force, but the car is not burrowing into the road. The road is always going to adjust to all the downward forces, and it's going to produce just the right amount of normal force to balance them because it's not accelerating vertically. So what's the advantage in terms of physics? What's the advantage of that fin? What's it increasing that's so important? The normal force, right? Now the normal force is not just being generated by the weight of the car, it's being generated by the weight of the car plus the downward force of the fin. And normal force is key because normal force is related to the frictional forces. So you get more static frictional force to go around that corner, right?
So you don't
If you have a
drift,
fin on your car than if you don't.
and you wouldn't drift as much, would you?
That's the point. Yeah, you wouldn't drift. You wouldn't slide because the rolling static frictional force is going to be higher, right? So there's some maximum speed without a fin where and we haven't talked about circular motion yet, but when we do, we'll call this the centripetal force. The force that's required to make you turn is not going to be sufficient, right? Because you don't have enough normal force to generate a longer friction vector, right? Okay? So those fins really, they're not just for looks. I mean, they probably are mostly for looks, but I don't know how valuable they really are. I'm going to say work,
Can we have a
but
problem where we calculate how much nominal force it would require to keep a car
Oh, we will.